In this talk, I will present our work, Multitask Learning Strengthens Adversarial Robustness. I'm Cheng Zhimao. This is a joint work with Amuk, Vikram, Vaishakhi, Shuran, Junfeng, and Kao. We are from the CS department at Columbia University. Today, all computer vision systems are vulnerable to adversarial attacks. After adding some invisible noise, the model predictions are subverted. We don't know what causes adversarial examples and still an open problem to fix it. In the last few years, the adversarial robustness for deep learning models has been rigorously investigated. We know typically deep learning models contain the input data, the model, and the output. One-line research shows that input data affect models' robustness, such as adversarial training, or using unlabeled data, or decreasing the input dimension. Another line of research shows regularizing models can also increase robustness. Possible networks constrain the least phase constant of neural network. Our previous work, TLA, used triple loss regularization to increase robustness. This paper investigates a new line of research based on the output of models. How the number of training tasks impacts adversarial robustness. We are interested in evaluating the robustness of multitask models because first, more and more applications of current machine learning call for models that can solve complex tasks and multiple tasks at once. Second, multitask learning is efficient for solving several tasks. And lastly, the robustness of multitask learning is not investigated. We first empirically show that multitask learning improves robustness for individual tasks. We then, both theoretically and empirically, show attack difficulty for multitask learning compounds as there are more tasks to be attacked. We conduct experiments on two datasets, cityscapes and taxonomy, and run experiments on up to 11 tasks, including segmentation, depths, key points, etc. Our adversarial attacks use the standard P non-bounded attack. We define the adversarial vulnerability of a classifier to be the maximum loss change by any noise within the perturbation bound. Please refer to our paper for formal definition. We measure the robustness of multitask models under two types of attack, single task attack and multitask attack. The single task attack fools one specific task, where the adversarial attack is optimized solely for that task. For multitask attack, it fools several tasks at once. We first empirically analyze the multitask model robustness under single task attack. We show an attack on cityscape segmentation as an example. Given a driving scene from cityscapes, the single task model is trained only on segmentation tasks. The adversarial attack for segmentation fools the segmentation model by adding walls and sidewalks to the road. For multitask learning, we add input reconstruction as an auxiliary task as an example. Then, a single task attack is launched solely for segmentation. After multitask learning on the right, some vulnerabilities of the road segmentation are fixed. This example shows that multitask learning increases the model robustness when a task is attacked individually. Besides the example we studied, we show quantitative results on cityscapes. In the table, by simply training segmentation with the reconstruction task, the robustness improved by 1.2 points on MIOU score. On training depths, by training depths with segmentation, the robustness for depths improved by 11%. On the taxonomy dataset, we further conduct multitask learning, combining 11 different tasks, including segmentation, depths, key points prediction, and so on. We train the row task as the main task, and the column task as the auxiliary tasks, and do single task attacks on the row task. The green color shows the model is more robust than single-task baseline. Multitask learning improved the robustness of 90 models out of the total 110 combinations compared with single-task learning. All the experiments before are conducted without adversarial training. Given that adversarial training is the most widely used way to improve robustness, we also combine multitask learning with adversarial training on cityscapes dataset. After training segmentation with steps, the robustness for segmentation increases by 2.4 points on MIOU metric. The depth task increased robustness by 8% after training with segmentation. Thus, multitask learning complements the adversarial training by improving both the clear accuracy and robust accuracy. The second type of robustness is the model's overall robustness measured under multitask attack. We show both theoretical and empirical results. Multitask attack fools several tasks at once. Thus, perturbations are optimized to fool several tasks at once. We first conduct theoretical analysis for the robustness under multitask attack. Using the first-order approximation, we show adversarial vulnerability is proportional to the Q-norm of the input gradient. The joint gradient is the sum of individual gradients for each subtask. Our theorem shows the overall adversarial vulnerability under multitask attack will be improved if there are more tasks and less correlated tasks added. Intuitively, with many uncorrelated tasks, perturbations needed to attack different outputs cancel each other out, which reduces the strength of the attack. Ideally, if all the tasks are independent to each other, the adversarial vulnerability of the model will decrease at the speed of 1 over root of the number of the tasks. We then validate the theory with empirical evidence. Segmentation predicts the category for each input pixels. By treating each pixel as one task, we show robust accuracy increase as more pixels are attacked. We measure the vulnerability with the norm of the gradient. In figure A, the vulnerability decreases as the output dimensionality increases. In figure B, the robustness accuracy increases as the output dimensionality increases. This explains why segmentation is more robust than classification, because it has a higher output dimension. We also validate the robustness of multitask attack by increasing the number of different training tasks on taxonomy dataset. We show the model's vulnerability, indicated by the norm of the input gradient, decreases as more tasks are attacked simultaneously. We also measure the actual robust performance. In the figure, blue line is the performance of the single task baseline. We use different strengths of attack to measure the robustness. We increase the perturbation bound from 1 to 16. We can see the blue single task model performs worse than the multitask model under attack. Thus, the overall robustness increases as more tasks are attacked together. To conclude, we show adversarial attack difficulty increases as the number of target tasks increase, which explains why segmentation model is more robust than classification. We also show multitask models improve the robustness of individual tasks compared to single task learning. Our work suggests that deep models are vulnerable to adversarial attacks partly because they are trained on too few tasks. Thank you for listening.